The ceiling for deep learning isn't computing power, it is data transfer. While the throughput of modern GPU processors has scaled exponentially, the bandwidth connecting those processors to the main memory has effectively flatlined. We call this the memory wall. This animated equation shows the standard scale dot product attention mechanism. To process information, a transformer multiplies query and key matrices to generate a distinct similarity matrix, which then runs through a softmax function to output a probability matrix. The dimensions of these intermediate matrices are dictated by the sequence length, denoted as n. When you feed a longer document into the model, the memory required to store those intermediate calculations scales quadratically. In a standard implementation, these massive n by n blocks must be materialized and written to the GPU's high bandwidth memory, or HBM. Reading and writing this sheer volume of data instantly consumes all available bandwidth, stalling the compute cores while they wait for data to arrive. Earlier architectures tried to bypass this by using sparse or linear attention. Those methods simply approximated the attention matrix, skipping calculations to save space, which degraded the quality of the model's output. Scaling context length without losing mathematical exactness requires an algorithm that targets the data movement bottleneck directly, rather than compromising the math. Designing an algorithm to solve this requires I/O awareness. An I/O-aware algorithm explicitly calculates and minimizes the physical cost of moving data between different tiers of a hardware system. This schematic maps the architecture of a modern GPU. The main memory, the HBM, holds tens of gigabytes of data and moves it at about 1.5 terabytes per second, but it sits across a physical chasm from the actual compute cores. Directly on the chip, touching the cores, is the static random access memory, or SRAM. It operates at a blistering 19 terabytes per second, but it is severely constrained, capping out around 20 megabytes of capacity. Standard attention ignores this hierarchy. By treating matrix multiplication, softmax, and output multiplication as isolated steps, the algorithm constantly forces intermediate data to take the slow round trip back and forth across the HBM data bus. Optimizing for modern silicon means minimizing the physical distance data must travel before it can be processed. This diagram illustrates FlashAttention's first structural shift, tiling. Instead of processing the massive query, key, and value matrices whole, the algorithm slices them into specific subblocks. These blocks are sized with precision to ensure they fit entirely within the GPU's strict 20 megabyte SRAM limit. Once the data is inside the SRAM, FlashAttention executes kernel fusion. It merges the separate mathematical steps into one continuous hardware operation, calculating the intermediate results locally. The algorithm iterates through every tile in the sequence and only writes the final output matrix back across the slow HBM bridge. Constraining the active data footprint to fit the ultra-fast on-chip cache completely eliminates the intermediate read and write bottlenecks. Tiling introduces an immediate mathematical problem, shown here. The standard softmax function requires the sum of exponentials across an entire row to calculate its denominator. If you are processing in isolated tiles, you don't have the full row. To solve this, FlashAttention utilizes an online softmax technique. As the algorithm loads and processes each block, it tracks two running statistics, the maximum value seen so far and the current sum of exponentials. When a newly loaded tile contains a number larger than the previous maximum, the algorithm triggers a dynamic rescaling mechanism to adjust the historical math. By multiplying the previously accumulated output by e to the power of the old maximum minus the new maximum, the denominator is retroactively updated without reloading the old data from the HBM. This continuous adjustment ensures that the final tile yields an output mathematically identical to a standard softmax processed over the full sequence. You do not need to compute everything at once to achieve exactness, provided you correctly track and apply historical limits to localized data. This visual contrasts how frameworks handle the backward pass during model training. Standard architecture saves the massive intermediate matrices in HBM during the forward pass, so they can calculate gradients later. FlashAttention actively deletes those intermediate matrices. It stores only the final output and a small linear vector containing the softmax statistics. When it is time for the backward pass, FlashAttention uses those stored statistics to selectively recompute the attention blocks on the fly, directly inside the SRAM. It also simplifies the softmax gradient calculation, using a scalar row sum to resolve the derivative locally, without requiring vector reductions across the entire sequence. Because the SRAM computes at 19 terabytes per second, while the HBM crawls at 1.5, executing the complex mathematics a second time is significantly faster than moving the saved data once. This table illustrates the final theoretical result. FlashAttention reduces memory complexity from an exponential O of n squared to a flat O of n. Crucially, I/O complexity and HBM accesses drop to an optimized formula dictated by M, the specific size constraint of the SRAM. In practice, this theoretical optimization produces a 1.5x to 3x end-to-end wall clock speedup for training deep learning models. By neutralizing the quadratic memory penalty, this single algorithmic change expanded industry context limits from 2,000 tokens in 2022 to the 1 million plus token windows operating today. The architecture continues to evolve, with FlashAttention 2 optimizing parallelization across processing heads, and Flash decoding applying these same tiling principles to the autoregressive generation phase. Scaling artificial intelligence relies on software that explicitly accounts for the physical constraints of the silicon it runs on.